Hello students, welcome back to my channel. So today we will discuss here about the next chapter of Unit 7. The name of chapter Thermal Properties of Matter, in which we will discuss here about what is the definition of heat and temperature, and after that we will discuss here about the measurement of temperature in Kelvin scale and in Celsius scale and also Fahrenheit scale. So after that we will talk here about the different type of thermal expansion, in which we will calculate the coefficient of thermal expansion alpha, beta, gamma, and then we will discuss here about the ratio of alpha, beta, gamma, what it will come. So here the chapter name is Thermal Properties of Matter. So the first topic which I will discuss with you is heat. When you will explain about the definition of heat, it is the type of energy, it is the type of energy which is the sensation of warmth. Clear? After that, as we know that here the difference about the heat and temperature is little. Here the heat is the type of energy which is the sensation of warmth, and here the temperature is the measurement of coldness. Temperature, when we define here about, it is, you can write the temperature of a body. Temperature of a body is the measurement of hotness or coldness of the body. Point clear? So this is called a temperature. Now after that, when here we are talking about, as we know that we are talking here about the measurement of hotness and coldness is called temperature. So when we use the measurement scale of temperature, so we have basically here three type of measurement scale which we will discuss here. Now for the measurement scale of temperature, we need two fixed point of reference of a body. Two fixed point of reference is required or is needed for the measurement of a body, or you can say the measurement scale. For the measurement of scale, or you can say measuring scale, or the measurement scale. For which the physical phenomena always occurs at the same temperature. So here we have two fixed point. You can say ice point and steam point. Are two fixed points for this condition, and these are known as freezing point So here I am writing the all things about the measurement scale of temperature. As we know that here first Celsius scale, known as centigrade also, centigrade scale. Second, Kelvin scale, Kelvin temperature scale. Third is Fahrenheit scale. So we have these three type of scale which we use for measuring the temperature, and I am writing here in short. In case of Celsius scale, when we talk here about the lowest point for this Celsius scale is 0 degree Celsius, and highest point of this Celsius scale is 100 degree Celsius, which is here freezing point and boiling point, and below this, in between this, 100 equal parts are there. And after that, when we talk here about the Kelvin scale has lowest point at 273 Kelvin. It is basically 273.15 Kelvin, absolute 0 point. But here for our calculation, or for you can say the numerical portion, generally we will take here 273 Kelvin as their lowest point, and the highest point is equals to 373 Kelvin. And after that, Fahrenheit scale, the lowest point is 32 degree Fahrenheit, and the highest point is 212 degree Fahrenheit. So here we have 180 equal division in between them, and here also we have 100 equal division as in Celsius scale. Point clear? So after the discussion about the Celsius scale, which is also known as centigrade scale, Kelvin scale and Fahrenheit scale, we will write the rough diagram of these scale, in which we will show their absolute temperature and also about the least and highest value of temperature. So see here, this is the division which I am representing here. So this is the Celsius scale. Point clear? This is the Kelvin scale. This is the Fahrenheit scale. Now see, as I have written here, 0 degree Celsius is the freezing point for the Celsius scale, and 100 degree Celsius is the highest, and in between them 100 equal divisions are there. And similarly, when we talk here about the Kelvin scale has 0 Kelvin, or you can write here, if you want to write 0 Kelvin into the value of degree Celsius, you will write here 273.15 is equal to 0 degree Celsius. Means at 0 degree Celsius temperature, the temperature in Kelvin is 273.15 Kelvin. So here I can write numerically, generally we will use, in place of 273.15, we will use generally 273 Kelvin. So here the freezing point is 273 and the boiling point is 373 Kelvin. And after that, when we write here about the Fahrenheit scale, it is 32 degree Fahrenheit as I have written here, and this one is 212 degree Fahrenheit, and in between them 180 equal parts are there, and in between them 100 parts are there. 100 equal parts or equal division for making the temperature, and 100 parts also and 180 equal parts. Okay, you can take the difference between them. After that, when we want to write here absolute temperature of them, absolute temperature case, the absolute temperature for the Kelvin scale is 0 Kelvin. Point clear? 0 Kelvin is called absolute temperature in Kelvin scale. So it means that in centigrade scale or Celsius scale, it will be 273.15 degrees Celsius. And similarly, when we want to write here about this condition, so it will be what? It will be supposed to, we can write here, it will be minus 459.69 degree Fahrenheit. So this is the value of absolute temperature in different type of measurement scale. After that, we can write here about the relation between the Celsius scale, Kelvin scale and Fahrenheit scale. We have much more scale, 2 more scale also, but here we will talk about only 3 basic. Point clear? So for next topic, pause the video and note down. So after discussion various type of measurement scale of temperature, so here we know that we have discussed Celsius scale, Kelvin scale and Fahrenheit scale. So I will give a relation between all scale. Remember this relation between all scale measurement. So it is, when we talk here about Celsius scale, it is T is a temperature in Celsius scale and 0 is their what? Freezing point temperature, and here total 100 equal divisions are. Similarly, when we want to write here about Kelvin scale, is the Tk is any random temperature of it, and it will be, the freezing point is 273.15 in actual, otherwise we will take here 273 only. So it is 273.15 Kelvin over 100 division. And similarly, Tf Fahrenheit scale, it has freezing point 32 degree Fahrenheit and divisions are 180. So this is the value of, or you can say the relation between the Fahrenheit scale and temperature, Fahrenheit scale, Kelvin scale and Celsius. So you can easily change the temperature from one scale to another scale with the help of this relation. Point clear? If you want to change any Celsius scale temperature into Fahrenheit, you will use this temperature, 0 degree Celsius is here. So similarly, you can easily change the other temperature in this form. Supposed to be here, let we want to change 0 degree Celsius into Fahrenheit scale. As we know that it will be 32 degree Fahrenheit. Let's see, Tc minus 0 degree over 100, we will use this at this relation, 100 is equals to Tf minus 32 degree Fahrenheit over 180. Point clear? So after that we will use here 0 degree Celsius. So see, Tc is the 0 over 100. Here Tc is equal to 0 degree Celsius is equals to Tf minus 32 over 180. So it will be 0 multiplied by 180, 0. So here Tf is equals to 32 degree Fahrenheit. So in Fahrenheit scale, 0 degree Celsius is equals to 32 degree Fahrenheit. Point clear? Similarly, you can do the Kelvin scale also, and in place of 0 degree Celsius, if you will put any other temperature like 1 degree Celsius, 2 degree Celsius, then you will get a different value of temperature. Point here. So after that, we will write here about the thermal expansion. We will write here about the next topic, thermal expansion, in which we will see that on increasing the temperature, the next topic is thermal expansion, in which we will talk here about the different modes on which the temperature, which are dependent on temperature. So first is linear expansion, second is area expansion, and third one is volume expansion. As we know that here, on increasing the temperature, if suppose to the length of a body increases, then this kind of expansion is called linear expansion. And on increasing the temperature, if the area of the body increases, then this type of linear expansion is called area expansion. And on the other hand, similarly, if the volume of a given body increases on increasing the temperature, so this kind of temperature is called volume. This kind of expansion is called volume expansion. So here, as we know that, so here I have written the value of thermal expansion, linear expansion, areal expansion, and volume expansion. And as we know that here, when we talk about different type of expansion, so we have first linear expansion. What is the meaning of expansion, and why we are talking about the expansion? Because this expansion is totally dependent on temperature. On increasing the temperature, if supposed to be a body having some given length, so if suppose the body has some length, and in place of length, or you can say as compared to length, the other dimension of the body are negligible. So that time we will talk here about only on linear expansion. Other dimension means their width, their height, or the other things. So here we are talking about linear expansion. If suppose a body of length L, if a body or an object of length you want to write L, and on increasing the temperature, it is understood on increasing the temperature, their length, because here we are focusing about the linear only, their length increases from L to L plus delta L. Therefore, in this condition, the increase in length depends on which value? These are depends on first increase in length depend on the initial length of a body. Point clear? Second, the increase in length depends on the change in temperature of a body. Initial temperature is supposed to be T1, and on increasing the temperature from T1 degree Celsius to T2 degree Celsius, the change in length is delta L. So it will depend on this also. So from first inequality, first relation and second relation, we can write here delta L is proportional to L delta T. And when you will remove this proportionality sign, so you will write that time a proportionality constant which is here alpha. Listen here, this is proportionality constant, this one is a alpha into L into delta T. Point clear? So it implies that alpha is equals to delta L over L into delta T, or L into delta T. You can write like that. Here alpha is called proportionality constant, is called proportionality constant, known as linear coefficient of linear expansion of linear expansion. Point clear? Now after that we will write here about the definition of this coefficient of linear expansion. So how I will write it? If suppose if we have L is equals to 1 unit, point clear, and supposed to be delta T is equals to 1 degree Celsius, and here if you want to write the formula, alpha is equals to delta L is equals to L into delta T. So if you will substitute the all values here, you can write alpha is equals to delta L into 1 degree Celsius. So it implies alpha is numerically equal to change in length. So we can define it. Coefficient of linear expansion. Coefficient of linear expansion of a body or a wire or a rod is numerically equal to the expansion or equal to the increase in length, increase in the length of a body of unit original length So we can define it. Therefore, coefficient of linear expansion is numerically equals to the change in length of the body. Here the body is solid, as we know that. Numerically the change of length of a body per unit length on increasing the temperature by 1 degree Celsius. So this is the definition of here linear expansion. And after that we will write here about the area expansion and volume expansion. So for that pause the video and note down. Now after the discussion about the linear expansion, here the next topic is area expansion. Listen one thing, here we are talking about the expansion in linear length, area and volume on the basis of temperature. So as we know that on increasing the temperature, the shape and size of the body changes. Initially we know that. So on the basis of this concept, we can define the different modes of expansion on the basis of temperature. So here one dimension mode when we have discussed, then we have discussed about the linear expansion. Here we are talking about the 2-dimension mode, in which supposed to be I have a square or cubical square basically, in which I have a rectangular or square shape of object which have here some length and some breadth also, and after that this is the area of that particular object. Point clear? So here we are talking about the area, the definition and other things. All are remain same as the previous, but here the coefficient of thermal expansion will be changed, because here we are talking about the areal expansion or area expansion, so we will use the other coefficient of temperature, which is called coefficient of area expansion, beta. So here we can say directly, as we know that initially on increasing the temperature, area will also increase as the as the length of the body. In previous condition, if you want to see the whole explanation in case of diagram, then supposed to be this is our length L from this side to this, and on increasing the temperature, supposed to be the length of the body or given wire is increases from L to delta L. So the total length is what? The total length is L plus delta L on increasing the temperature. So here this expansion depends on temperature, as I have discussed, denoted by means this delta L proportional to L, this delta L proportional to T is it is temperature change, and after that we will get the value of alpha delta L over L of T delta T. So similarly here we will also discuss about the area expansion, in which we can write here if A be the area, A be the initial area, because it play an important role for this derivation. Initial area of the rectangular body. Here I am taking rectangular body, but when we want to show the relation between alpha, beta, gamma, then we will take a cube body for easier calculation, or square body, cubical body in 3D, square body in 2D for easier calculation. So here A is a initial area. So now on increasing the temperature, if area changes from A to A plus delta A, that time therefore change in area is directly proportional to it. It will also depend some physical quantities. So it depends on first the initial area of the given 2D or two-dimensional object, which is here square. You can consider it rectangular initially. So, and second delta is directly proportional to change in temperature. Suppose initial temperature is T1 degree Celsius and final is T2 degree Celsius, then change of this temperature T1 minus T2, because here we are increasing the temperature. So initially we know that T2 is greater than T1, so we can write this change in temperature T2 minus T1. So this difference is equal to T degree Celsius supposed to be. So that time this depend on this value. After that we will write these two in this format. Point clear? So we will see that on removing this proportionality constant, I will use beta A into delta T. So beta is equals to delta A upon A into delta T. So now from this calculation we will get the value of beta. Here beta I consider as proportionality constant known as areal expansion, coefficient of areal expansion. Here beta is known as, I am writing direct, it is proportionality constant, as we know that, known as area, coefficient of areal expansion. Coefficient of area expansion. Point clear? So this one. And after that we will talk here about the third case, in which we will discuss here about the volume expansion. Then after we will talk here about the relation between alpha, beta, gamma, which are the coefficient of linear expansion, coefficient of area expansion, coefficient of volume expansion, and which will be equals to 1:2:3. How it will come? It is very interesting. So let's see. Now after discussion the area expansion, here the next one is volume expansion. Volume expansion. On increasing the temperature, here we will see how the volume of the body changes or increases. So for that I will consider here again a cuboidal body initially. For that, supposed to be a three-dimensional object, have some initial volume V, and on increasing its temperature from T1 to T2, supposed to be T2 greater than T1. So then we will see that their volume increases from V to V plus delta V. So here we will talk about the change in volume. So initially I am writing the statement here. If V is the initial volume of the body, and on increasing the temperature let its volume changes from V to V plus delta V. Okay, therefore, for expansion of volume, we can write change in volume depends on these values. First, directly proportional to the initial volume of the body. Second, directly proportional to the change in temperature, as the previous conditions we have done. So from these two, we will write here delta V proportional to V into delta T. Point clear? And delta V, when we want to write after removing this proportionality constant, I will use here proportionality constant. After removing this proportionality sign, I will use here proportionality constant, which is gamma, like this. So gamma into V into delta T. So the gamma is equals to delta V over V into delta T. So this gamma is nothing, it is a proportionality constant known as volume, coefficient of volume expansion. I am writing here gamma is known as coefficient of volume expansion. Point clear? Now, these are the values, and here note one thing. SI unit of all type of coefficient of proportion. Coefficient of proportionality symbol means here coefficient of thermal expansion. I will use the word thermal expansion. Either it is alpha or beta or gamma, is, you can see from here, degrees Celsius with inverse. Degrees Celsius in inverse. Point clear? So this is the value and the derivation of all kind of thermal expansion.